Hello everyone, this is Yan Hao. Today I'm going to present our work BGPQ, which is heap-based priority queue implementation on GPUs. A priority queue is an abstract data type that each element has a certain priority. The priorities of the elements determine the order in which the elements are retrieved from the priority queue. A priority queue usually supports two operations, called insert and delete min. Insert operations insert an item into the queue together with its priority, while delete min removes the item with the highest priority from the queue. The priority queue plays an important role in many well-known algorithms, including Dijkstra's algorithm, A-star search in artificial intelligence, and the branch and bound problems. A concurrent priority queue is intended to be accessed simultaneously by multiple processors. Concurrent priority queues for multiple core GPUs have been extensively studied in the literature. There are different implementations that are based on different data structures like heap and skip list, which we'll talk more later. There are also other alternative data structures like MD-list, which use our multi-dimensional linked list to implement a priority queue. CBPQ is another implementation that uses a linked chunk list, which performs well under high contention. However, there are very few work studies the concurrent priority queue for many core GPUs. The first generic priority queue implementation for GPUs is provided by Hurst Group. They propose a heap-based implementation, however, it only supports pipeline parallelism, whereas different types of parallelism can be explored on GPUs. There is also GPU-friendly skip list implementations in the literature. In Moscowitz work, the skip list is partitioned into chunks and the lookup is performed in parallel within each chunk. However, it does not support the delete min operation and is not a real priority queue. In the following of this presentation, I will first describe several priority queue designs on CPUs and then analyze their friendliness to the GPU execution model, which leads to our BGPQ design choices. Let's first talk about different data structures used to implement the priority queue. Early designs of concurrent priority queue have mostly been based on heaps. Nekshawara and Kuma proposed a fine-grained log-based heap implementation in the 1980s. Later, Han's group improved it by applying a bottom-up insertion and spreading the subsequent insertions through a bit reverse technique to minimize the conflicts. Heap-based priority queues have big O log n performance for both insert and delete min operations. From a space complexity standpoint, it needs n plus big O1 space, since nodes in the heap can be stored as an array, while here n is the number of nodes in the heap. A severe limitation of heap-based implementation is the scalability. A global lock of the heap size is usually required, which all operations must obtain first. Also, the root node is usually a bottleneck that may be potentially accessed by all operations. In recent years, skip list-based implementations have become the focus of modern concurrent priority queue research. A skip list is constructed with a hierarchically ordered linked list. The bottom layer linked list contains a sorted sequence of all keys. A key will appear in the next level with certain probabilities. Shavit and Lawton were the first to propose a skip list-based priority queue. In their work, a crucial observation is that as soon as a node has been successfully inserted into the first level, we can guarantee the correctness of the data structure. Therefore, both insert and delete min operations can be split into steps to avoid contention on the same level. Sundell and Sigas proposed another skip list-based priority queue that is lock-free. They also show that their implementation is linearizable. One of the most recent work was published by Linton and Johnson that matches physical deletions. Their design elevates the contention on the head nodes in the skip list and achieves a speedup of around 30% to 80% compared with other skip list-based implementations. Skip list-based implementations also have an average big O log n computation complexity, but considering space complexity, it requires more memory space than the heap, as keys need to be stored at different levels of the skip list. Moreover, a skip list is a dynamic data structure that uses linked lists as it grows and shrinks at runtime. In consequence, dynamic memory allocation and reclamation are required. To make a skip list priority queue implementation be scalable, the memory management scheme itself needs to be scalable. When designing a concurrent priority queue on GPUs, we believe that heap is more favorable than others. There are two reasons. First, although GPU memory has more than 10 times throughput than CPU memory, its resource is scarce. When running out of memory on the GPU, it needs to transfer data back and forth between CPU and GPU, which will cause a memory bottleneck. Second, concurrent GPUs do not have such a good dynamic memory management as that on CPUs. Dynamic memory management itself is non-trivial to be parallelized on GPUs for general cases. As a result, we use Heap as the underlying data structure in our BGPQ design. Next, we explore different parallelism in concurrent priority queue implementations. Most existing works explores only the task parallelism. A task parallelism means that both insert and delete main operations can be executed simultaneously. Very few studies for concurrent CPU implementations have explored data parallelism. Do and process propose the only concurrent CPU heap implementations that we know explicitly explores the data parallelism. It expands a node to store multiple keys and move multiple keys at once. Hurst's work developed a natural extension of do and the process work to GPUs. However, their method requires to insert or delete a fixed number of keys at once. While the GPU skip list by Moskowitz explores data parallelism in the lookup stage, a concurrent priority queue implementation on GPUs must support both data and task parallelism. Modern GPUs are equipped with hierarchical parallelism. It is task parallelism at coarse-grained level, and at the fine-grained level, it's also data parallelism. Another design choice we considered is the potential collaboration between different operations. Existing studies have proposed different ways to let threads collaborate rather than content for shared resources. For GPUs, it's important to have both the thread collaboration features, while in the meantime avoid problems such as thread divergency, memory uncoalescing, and memory resource contention. Here's a summary of what we have discussed before. It includes different priority queue implementation features and BGPQ's comparison with existing implementations. So we propose BGPQ, a heap-based GPU priority queue implementation. Here B stands for batch, which a node in the heap contains more than one keys. We also apply different thread collaboration methods to BGPQ and show that BGPQ is linearizable. Due to time limit, I won't discuss the thread collaboration and the linearizable proof here. If you are interested, I will suggest you read our paper. As I mentioned before, BGPQ uses a heap as the underlying data structure. In this presentation, we use a main heap as an example. Each number represents the priority of the item, which is a key. So each node contains k keys, except the root and the buffer node, which are used to support insert or delete less than k keys. The buffer node is used to store the keys that need to be inserted but have not accumulated to k keys. Later I will show an example. The smallest keys in each node must be larger than the largest key of its children to maintain the heap properties. So now let's first discuss the insert operation. In BGPQ, we can insert any number of keys. Our insert operation follows a top-down manner that starts from the root node. Insert keys are sorted first and then merged with the root node. The smallest parts are placed back into the root such that the root always contains the smallest keys in the heap. If the buffer can hold all insert keys, updated insert keys will be placed directly into the buffer. Otherwise, an insert heap file will be triggered. In this way, using the buffer node multiple insertions operations may trigger only one expensive insert heap file process and can reduce the heap file overhead. In the insert heap file process, it first determines the target node and then traverses the path from the root to the target. For the delete bin operation, just like insert operation, BGPQ can also support delete any number of keys from the heap. If the root contains enough keys to delete, they are retrieved directly. Otherwise, a delete bin heap file will be triggered when the root becomes empty. The keys in the last node will be placed in the root and start the heap file process. You can read our paper to see more our implementation details. We also open source BGPQ and the link is provided in the paper. We compare BGPQ with 4 CPU baselines, entire thread building blocks TBB, chunk-based priority queue CBPQ, and 2 skip list-based implementations, Linden and Johnson skip list and Spurious the relaxed implementation. We compare with one GPU baseline, which is Hertz heap-based implementation. We call it P-Sync. We first discuss design choice of BGPQ. We vary the thread block size and batch capacity, which is K in this presentation, and the number of thread blocks. We show the performance of inserting 64 million random 32-bit keys into an empty heap and then deleting all keys. Here, the thread block number is the number of working processors that perform insert and delete min operations. The maximum batch capacity we used in this experiment is 1024 keys. In figure A and B, we show the performance with varying BGPQ node capacity and thread block size. We can observe that with the same thread block size, the performance becomes better when the node capacity is larger, as it provides more intra-node parallelism. In figure C, we show the relationship between performance and the thread block number. We see that the benefit from concurrency is restricted when the thread block number is more than 32, as the contention on the heap root becomes serious. Now we compare BGPQ with the other 5 priority queue implementations. We evaluate the performance of inserting 1 million, 8 million, and 64 million random keys into an empty priority queue, and then deleting all keys from the priority queue. The y-axis is the speed up of BGPQ compared with each different implementations. BGPQ is much better than all CPU parallel baselines. Spray list has the best performance since it's a relaxed skip list. LJSL does not scale under a large number of concurrent threads, thus the performance is not competitive. Compared with P-Sync, which is the only GPU implementation, BGPQ has an average of 9.3 times speedup. We apply BGPQ to a real-world implementation, A-star graph search, which is widely used in pathfinding and graph traversal algorithms. We're only able to compare BGPQ with TBB, SprayList, and LJSL due to implementation limits in other baselines. We use 3 different graph sizes with 2 different levels of obstacles. We can observe that BGPQ-based solutions are much faster than others with a 12 times to 46 times speedup. In conclusion, we study existing concurrent priority queue implementations and their corresponding GPU friendliness. We present BGPQ, a GPU-friendly priority queue implementation. We compare the performance of BGPQ with 4 CPU baselines and 1 GPU baseline and show significant speedup. Thank you for your attention. Any questions?